Welcome back, everybody. So in this video, we'll be looking at formulating a Taylor series for complex functions. So this will be similar to Taylor series that you've seen in calculus and real variables. Okay, so as you recall in I believe the last video I posted. We went over a power series in complex variables, right? A power series in complex variables. It looks like this: a sub k times z minus z naught raised to the k power, right? Z minus z naught raised to the k power. The a sub k are the coefficients of the power series. They're complex coefficients. And then z naught is the center. Is the center of the power series, right? Okay. Now the goal here is to formulate a power series representation for a analytic function, right? And whose circle of convergence is the following, I'll say. Right? Oops. Z minus Z naught is less than capital R. Okay. And a couple of remarks about power series. As you notice, the formulation of a power series, it's just a polynomial. Okay. So you can differentiate the power series or integrate a power series term by term. Okay, and it will still yield the same circle of convergence. Okay, so a couple of remarks about power series is, well, first, a power series forms a continuous function. We'll call it f of z with circle of convergence. Z minus z naught is less than r. The second remark is that a power series can be differentiated term by term. But then its circle of convergence. Okay. The third remark is that the power series, any power series, can be integrated term by term. And what I mean by integrated is we're looking at a line integral of a curve inside the circle of convergence. Okay, so this is within the circle of convergence. Um, and you can do this for every contour. C lying entirely in the circle. Okay, so so you can differentiate and integrate uh, power series term by term, and it will give you another power series that will yield the similar radius and circle of convergence as the original. Okay, so which I'll label this as f of z. Okay, now the goal here is, if we are given an analytic function, can we formulate a power series which relates to the function that was given? Um, so, suppose we have a a analytic function f of z, and let's say the nth derivative at z naught exists. Okay, so at a point z equals z naught. Okay, this notation indicates the nth derivative, and where n is equal to 0, 1, 2, 3, so on, right? So it's infinitely differentiable at z naught. Okay, so we're going to suppose that f of z is equal to a power series, right? Centered at z naught. Okay, z minus z naught squared plus a3 times z minus z naught cubed, and this series keeps going, right? Now, if we plug in z equals z naught, right, each of these terms will cancel since there is a z minus z naught occurring. So you'll get that f of z naught is equal to a0. It's pretty straightforward. Next, if I differentiate f of z, well, I'll just get a0 is a constant, so it's 0. So I'll get a1 plus 2 times a2 times z minus z naught plus 3 times a3 times z minus z naught squared plus, and this keeps going, right? So we differentiate the power series term by term. Okay. At z naught, f prime at z naught is equal to, so in this case, these quantities right here would be 0, right? And we will get that that f prime of z naught equals to a1. Okay. If I take the second derivative of the power series, well, a1 is a constant, so that would be 0. And then I'll get 2 times a2 plus 3 times 2 times a3 times z minus z naught plus, and just keep going with this series, differentiating the previous function term by term. And if we plug in the second derivative at z naught, this equals to 2 times a2, right? And if you keep going, we may see a pattern. So f triple prime of z, it will be 3 times 2 times a3. Okay. And then you'll have plus 4 times 3 times 2 times a4, right? Times a4 times z minus z naught plus yada yada yada. Okay. And f triple prime at z naught, this would equal to, I'm going to write this out as 3 factorial times a3. A bit of a review about factorials. So if I say n factorial, this is not an exaggerated n, it's pronounced n factorial, right? N factorial. This equals to n times n minus 1 times n minus 2 times, we go all the way down to times 3 times 2 times 1. So for example, 5 factorial would be 5 times 4 times 3 times 2 times 1, right? So in this case, it's 120, right? Okay, 120. So that's what a factorial is, okay? And so from here, we can solve for what the coefficients a sub n equal to, right? So we know that a1 is f prime of z naught. And this one, this says that a2 is equal to f double prime of z naught over 2. 2 times 1, or 2 factorial. This right here, this says that a3 is equal to f triple prime of z naught over 3 factorial. And I don't know if you can see a pattern, but the pattern here is that the a sub k coefficient, this would equal to the kth derivative at z naught divided by k factorial. And this is how you would get what is called the Taylor series centered at z naught. So the Taylor series of an analytic function f of z at z equals z naught, I should say centered at z equals z naught is, so we can express f of z as this sum, k equals 0 to infinity of the kth derivative at z naught divided by k factorial times z minus z naught to the k power. Okay. Okay, so if the Taylor series has z equals 0 as its center, it is called a Maclaurin series. And then a Maclaurin series is basically looks like this. 0 plus 0 I should say. So k factorial times z to the k power. All right, so this is what's called a Maclaurin series. Okay. And so this is part of what is called Taylor's theorem. Taylor's theorem. So this part right here, that's part of what's called Taylor's theorem. So you can use this theorem as long as f of z is analytic along a domain D. All right. And this would be, so this theorem is valid for the largest circle with the center Z naught and radius capital R. So that refers to the circle and radius of convergence. Okay. And a quick note to figure out the circle and radius of convergence is we can use either the ratio or the root test in the last video to uh, figure out the circle and radius of convergence. Well, not so much the circle of convergence, but most importantly, the radius of convergence, right? Um, uh, and then we'll go over this in the next video. So the radius of convergence, R, is the distance from the center Z naught of to the nearest isolated singularity. We'll go over what isolated singularity is in the next video. Singularity. Okay. All right. So as an exercise, I want you to compute the Maclaurin series for e to the z, and then sine of z, and then cosine of z. Okay. I want you to work on these for a bit. So really, you're just using the definition of the Maclaurin series, right? The Maclaurin series is this sum right here. So we want to figure out the Maclaurin series. Let me move these down here. So right there. And then, yeah, find the Maclaurin series for the following functions, okay? Okay, so I assumed you worked on this, these examples. These Maclaurin series is exactly what you would expect they're similar to the Taylor series for e to the x sine of x and then cosine of x in Calc 2, right? So e to the z, this would equal to 1 plus z squared over 2 factorial plus z cubed over 3 factorial plus z to the fourth over 4 factorial and so on, right? And so this representation is, it looks like this, z to the k over k factorial, okay? Sine of z, this would equal to x minus, I'm sorry, I'm talking about complex numbers. Z minus z cubed over 3 factorial plus z to the fifth over 5 factorial minus z to the seventh over 7 factorial plus this keeps going, right? And this series representation looks like this, right? The signs are alternating. The exponent numbers are odd on z, and the factorial number is odd as well, right? 2k plus 1 factorial. And then cosine of z is equals to 1 minus z squared plus z to the fourth over 2 factorials there. 4 factorial minus z to the 6 over 6 factorial plus, and this pattern keeps going. The series representation looks like this. Z to the 2k over 2k factorial. I'll write that up in parentheses here. Okay, 2k factorial. So those should be the Maclaurin series. Excuse me, the Maclaurin series for those three functions respectively. Okay, so that's important. So let's look out some examples. Okay. Expand. As the Maclaurin series. Part A, we have this function. 1 divided by 1 plus 2z squared. Okay. And then part B is cosine of z over 2. Okay. So I want you to look at how we would formulate the Maclaurin series for these two functions. All right. Okay, so I assumed you worked on these examples. So I'm going to put this second part off to the side. I'm going to have a lot of work here. So, okay, so for part A, we have, so this should be a plus, but really we want to look first about how we would formulate a geometric, a Maclaurin series for 1 plus 2z. Spoiler alert, this is a geometric series, like I said. This will represent a geometric series. So if I write out this quantity as 1 over 1 minus negative 2z, this should ring some bells about how we could express this quantity, right? So as you recall, a series 1 plus z squared plus z cubed plus z to the fourth plus yada, yada, yada. This equals to 1 over 1 minus z, as long as the absolute value of z is less than 1. Right, so this is just review in the last video about the geometric series on z. Okay, so we're going to use that fact here. Okay, 1 over 1 minus z is equal to that sum. All right, so 1 over 1 minus negative 2z. So minus 2z is the common ratio, right? Common ratio. Okay, so 1 over 1 minus negative 2z, that equals to 1, I'll just say plus negative 2z plus minus 2z squared. So we're plugging in negative 2z for every z we see in that geometric series, right? So plus negative 2z cubed plus minus 2z to the fourth, okay, plus so on. That's what it looks like term by term. So this equals to 1 minus 2z plus 2z squared minus 2z cubed plus 2z to the fourth, okay, minus so on, right? Okay, so what this series looks like is the sum from k equals 0 to infinity of minus 1 to the k, so it's alternating, times let's just write out 2 to the k, 2 to the k power times z to the k power. All right. So that would equal to 1 over 1 plus 2z. Okay, so hopefully that makes sense. But we need a power series representation for 1 divided by 1 plus 2z squared. Now, if you notice, if we differentiate with respect to z of 1 over 1 plus 2z, well, I'm going to rewrite it like this. So 1 plus 2z to the minus 1 power. Minus 1 power. So if we differentiate this, we're going to use the chain rule. And so this equals to minus 1 plus 2z to the minus 2 power. To the minus 2 power times 2, right? Okay, so the derivative, right, this would be minus 2 over 1 plus 2z squared, okay? And this has to equal to the derivative of the terms in the power series we formulated up here. And so this would equal to the sum when k equals 0 to infinity of the derivative with respect to z of minus 1 to the k times 2 to the k times z to the k, right? So if we differentiate functions, a constant gets eliminated, right? So we're going to have to do a shift index here. So instead of starting at k equals 0, we're going to start off at k equals 1. Okay, so hopefully that made sense. So this quantity, 2 over 1 plus 2z squared, this would equal to the sum from k equals 1 to infinity of, so this would be minus 1 to the k times 2 to the k times k times z to the k minus 1, right? Z to the k minus 1. So what we have here is, okay, so we'll have a minus 2z. And okay. Yeah, all right. So if I divide both sides by -2, I will formulate the power series of 1 over 1 plus 2z squared. And so this would be k equals 1 to infinity of, so 2 to the k. Right, okay. Just double checking. So 1 to the k minus 1, 2 to the k minus 1 times k times z to the k minus 1 power. Okay, let me write this bigger. So minus 1 to the k minus 1 times 2 to the k minus 1 times k times z to the k minus 1 power. All right. So, all right. So to figure out the, I guess the radius of convergence, right? We can use the ratio test. Ratio test. Divide by a sub k. So, okay. So that would mean, so this equals to the limit as k goes to infinity of, so we'll have a minus that's positive. So, so to the k, so we'll have a 1/2. And then we'll have a z to the k and a z to the k minus 1, right? All right, I'll just write it like this. So this would equal to the limit as k goes to infinity of, so I'll have a 1/2 times k plus 1 over k times the length of z. Okay, and so this would equal to the length of z over 2 is less than 1. Hold on a second. Okay. I know I made a mistake somewhere. Oh, okay, I see. I see my mistake. That should be not 1/2, but it's 2. Okay, 2 times length of z is less than 1, which means that the length of z is less than 1/2. Okay. Right, length of z is 1/2, which is exactly what we need, right? This has to be less than 1. So the length of z has to be less than 1/2 and should be the same when we differentiate the function. So, okay, good. All right, so hopefully that made sense. Yeah, hopefully that example made sense. So in part B, all we have to do is just look at the Maclaurin series for cosine of z term by term. So this is 1 minus z squared over 2 factorial plus z to the 4th over 4 factorial minus z to the 6th over 6 factorial. Okay. And it turns out if you use the ratio test for cosine of z, this function is entire, right? So this Maclaurin series will converge for every complex number, right? So the radius of convergence is infinity, all right? So all we have to do is just plug in z over 2 for every z we see in our series, right? So that would be 1 minus z over 2 squared over 2 factorial. plus z over 2 to the 4th over 4 factorial minus z over 2 to the 6th over 6 factorial plus, and this pattern keeps going, right? And so Lorentz series, it will look like this. So minus 1 to the k z over 2 to the 2k power divided by 2k factorial. Okay. And if you do the ratio test, right? If you do the ratio test, z over 2 over 2k plus 1, oh, shoot, raised to the 2k plus 1 power divided by 2 times k plus 1 factorial times 2 to the k 2k factorial divided by z over 2 to the 2k power. All right. And so you'll get the length of z over 2 squared times the limit as k goes to infinity of 1 over 2k plus 2 times 2k plus 1, and this is 0, right? So the series converges, right, for every complex number, right? So the radius of convergence is infinity, okay? Here's another example. Let me scroll down here. I want you to expand the function f of z equals 1 over 3 minus z as a Taylor series. Centered at z naught equals 2i. Okay, I want you to work on this example as well. Try to formulate a Taylor series for f of z equals 1 over 3 minus z at the point z naught is 2i. So try to work on that example. All right, so I assumed you worked on this example. Let's see how you would formulate it. Okay, so by definition of a Taylor series, right, we want to write out f of z as a sum of the nth derivative at z naught over, I should say, I'll say k here. K equals 0 to infinity of the kth derivative at z naught divided by k factorial times z minus z naught to the k power, right? So we have f of z as 1 over 3 minus z. So I'm going to write that out as a power. So 3 minus z to the negative 1 power. And then we're just going to take derivatives of that function. So f prime of z, this equals to minus 3 minus z to the minus 2 times negative 1. So this would equal to a positive 3 minus z to the minus 2 power. The second derivative of z, this would equal to minus 2 times 3 minus z to the minus 3 power times negative 1. So this equals to 2 times 3 minus z to the minus 3 power. Hopefully you'll see a pattern here at this point. F triple prime of z, so I'll do one more. So this is minus 3 times 2 times 3 minus z to the minus 4 times negative 1. And so this equals to 3 times 2 times 1. So I'll write that out as 3 factorial times 3 minus z to the minus 4. So hopefully you see a pattern. 2 times 1, that's 2 factorial, right? And then, so the fourth derivative, right? Well, it will look like this. So 4 factorial times 3 minus z to the minus 5, right? And so we can formulate we can get a formula for the kth derivative at z. So this would equal to k factorial times 3 minus z to the minus k plus 1 power in parentheses. Okay, so this is the formula for the kth derivative at z. All right. And so the kth derivative at 2i, that center was 2i. So this would equal to k factorial times 3 minus 2i to the negative k plus 1 power, right? So minus k plus 1 power. So the function, this would equal to this series, k equals 0 to infinity of, I hate that sigma. Okay. Somewhat better. Okay. So that would be, so the kth derivative at 2i, so that is k factorial times 3 minus 2i to the negative k plus 1 power all over k factorial. All right, times z minus 2i to the k power. All right, to the k power. So the k factorials will cancel, and we'll get the sum equals to the sum from k equals 0 to infinity of, okay, so I'll have 1 over 3 minus 2i to the k plus 1 power times z minus 2i to the k power. And this would equal to, I'll have an extra factor of 3 minus 2i, 1 over 3 minus 2i, and I will write this out as a sum from k equals 0 to infinity of z minus 2i divided by 3 minus 2i to the k power. All right. And so what we want to do is, okay, so this is our, so this is a geometric series. No, I was wrong. So, yeah, yeah, it is a geometric series. It's all that raised to the k power. So what we want to do is figure out the radius of convergence. So that would imply that this quantity in absolute value, so the absolute value of z minus 2i over 3 minus 2i has to be less than 1. And so this means that the length of z minus 2i has to be less than the length of this complex number, 3 minus 2i. The length of 3 minus 2i, well, that equals to the square root of 3 squared plus minus 2 squared. 9 plus 4, so that's root 13. So what that means is the circle of convergence would be this, right? And the radius of convergence is the square root of 13. Okay. So that's how you formulate the Taylor series of that function and determining its radius and circle of convergence. Okay. Now, I want you to work on these problems to check comprehension. So, page 289, 2, 8, 10, 12, 16, 19, 22, 26, and 31. Okay, suggested problems for you to work with. All right, so hopefully this video was helpful. In the next video, we're going to get into some crazy content. So we're going to be examining further on what are called singularities of complex functions. So they'll have isolated singularities or removable singularities, okay? And how we can formulate a power series if we are involved in a case where we have a singularity for a function, okay? So that will involve what are called Laurent series. So in the next video, I will describe in deep detail about Laurent series. So other than that, hope you like this video, and I'll see you next time.